Hello everyone. In the previous video, we started discussing the decrease and conquer type algorithms. And as you will remember, there are three types of decrease and conquer algorithm paradigms. So the first one is decreasing the size by a constant. So we discussed it in the previous video. And in this video, we will discuss decrease and conquer by a factor and by some variable sizes. Again, we have a couple of examples for those. And so let's start. You remember computing the power of A in the previous lecture as an example for decrease and conquer by a constant by 1. Now we would like to investigate by a factor. Okay. an is equal to a times a to the power of n minus 1. So this is decrease and conquer by 1. In the same way, what I can do is I can say that a to the power of n is equal to a to the power of n divided by 2 to the power of 2. And according to being even and odd, so you can have some small tweaks. Okay, this way, what happens is I started with an input size of n, then it turned out to be n over 2, right? And then it will turn out to be n over 4. At each step, I'm not decreasing the input size by a constant amount. I'm decreasing the size by a factor of the previous one. So in that case, it is 1 over 2. And in many cases, the factor for the decrease and conquer type algorithms is 1 over 2 something. Okay. Later, after those decrease and conquer type algorithms, we will start discussing divide and conquer type approach. And at that time, we will discuss the difference between these decrease and conquer and divide and conquer type algorithms. But here, there is again a nice sketch of by a factor approach. So I have the problem size of n. I make it a smaller size, let's say n over 2. I solve the smaller size problem, and then I will have the solution to mine. Okay. Drawings. The main example of decrease and conquer by a factor is the binary search. And you know, binary search is something we should all know very well. It is not very difficult and it's very intuitive. Once you have a sorted list of items and you are looking for a key, what I can do is instead of having a search, a sequential search, as we discussed in the brute force and exhaustive search videos, okay? Instead of scanning the array, what I can do is, since everything is sorted, I can go to the middle of this array and check whether the key I'm looking for is equal to this middle element or not. If my key is greater than this middle element, then I know I don't need to investigate anything on the left because these are all less than AM, which I know my key is greater than. That is why now my problem is whether that key appears on the right side. And I will repeat the same process. I will go to the middle. I will check it. If my key is less than this amount, then I will consider this part. Or if it is greater, then I will consider this part. Moral of the story is, once I check the middle element, I get rid of the load of half of the sequence. You either neglect this part or that part. That leaves problem size of n to be n over 2. This is the binary search. Here is an example of that. So I'm searching for key 70. Okay, so my key is equal to 70. So initially, I have a list of size 13, and I have this middle element here. How you compute it? So 0 plus 12 divided by 2 is equal to 6. So this is the middle element. We go and check this middle element with 70. We see that 70 is greater than 55. That means I'm sure that 70 is not here. Then I'm left with this part. Now my left index is 7, my right index is 12, and I would like to find the middle. Okay, so 7 plus 12 by 2. Okay, so this will give you the middle element as 9. Now I will compare 81 with 70. It turns out that my key is less than that amount, so it cannot be here. Good. Now I am left with this amount, so middle element becomes that one, and I check it and I find it. I am sure you all noticed that the number of steps involved in a binary search is log n, because at each step you just decrease the size of the problem by half. And here is the pseudocode of this binary search algorithm. We should all be very fluent with the binary search and know that it is a decrease and conquer by a factor, and this factor is equal to 1/2. What else I have? Here is another example, maybe less popular one. So that's the Russian peasant multiplication. How it works, I would like to compute n times m. The name is Russian peasant multiplication, so the book includes the story about this. So once you are interested, you can just go and see why people call this Russian peasant multiplication. Actually, according to the book, this multiplication procedure was being used very popularly in Russian peasants, but I don't know. Okay, so you can just go and check it. But just to make clear why the name is this. Okay, so I would like to multiply n by m. N times m is equal to n/2 times 2m. So that's very clear, right? However, for n/2 to be an integer, n should be even. So if n is even, no problem, I will do it this way. What will happen if n is equal to odd? If n is equal to odd, with some small algebraic manipulation, right? So you can write n times m in this way. So that means actually what I will do is n will become n minus 1 divided by 2. M will become 2m, and I will add an additional m value to this. Okay. Here is the pseudocode for that. It also includes the sign management, because you may be multiplying -5 with 6, or -5 with -6, +5 with +6, whatever. So that part is just dealing with the sign, not a big issue. But let's assume both of them are positive numbers. What we will do is this part. Okay, so there is n and there is m. We run this loop until n is less than 0. Okay, so we check if n is even or odd with this line. Okay, and if it turns out that n is an odd number, what I will do is I will increment my temporary variable by that amount. Okay, and then m will become 2m and n will become halved. Okay, so that's the floor function. But better to follow it on this example. Here is the case. I have this n value, m value, and r. R is initially 0, and at the end, r will include the multiplication result. What will happen is, so that is 11, that is 13. I start with the smaller one, so I choose this n, and I divide it by 2, okay? Dividing it 11 by 2 and taking the floor, so this will give me 5. At the same time, what I will do is I will double the m value. Since n is odd, what I should do is I should add m to the r. Okay, so by the way, I guess this should be not m, but m maybe. Okay. Anyway, so next step, I have 5. I will again half it to the 2. This is still an odd number, so that is why I will need to add 26 to current 13, so it will become 39, and I will double this 26. Continue. Now that is an even number, so I will not be adding anything to r. This will just become 1, and this will just become 104. And I still have r value to be 39. And 1 is an odd number, so that means I will need to add m to this r. So 39 plus 104, so it will make 143. Okay, and then m will be 208, so no worries. So actually I will stop here because n turned out to be 0, and this is my final value. Okay, so that's the Russian peasant multiplication operation. We see this as an example of decreasing the problem size by a factor, and as you see, this is again by a factor of 2. Okay. We have not very much examples about those decrease and conquer by a factor, and even variable size examples is limited, but there are a couple of famous classical examples, so I will just try to cover them with you. Okay, so the first one is, so now I will decrease the problem size by a variable amount, not by 1, not by 2, sometimes by 5, sometimes by 400, whatever. So okay, so that's a variable size. And let's remember the Euclidean greatest common divisor, right? So actually Euclidean common divisor, so you can do it in this way, or there is another version which runs with the subtractions. Both are fine, and both are good examples of variable size. So in this video, let me try to do something with, let's say, 40 and 40 and so let's make it not 40. I'm trying to select good numbers, and 42. Okay, so 30 and 42. So I will try to make 40 and 32 with this approach. Okay. Which one is greater? So 42 is greater. So that will turn out to be GCD, right? 30 and 42 minus 30. So that will be 12, right? And then this will go out to be GCD 18 by 12, right? And this will go GCD 6 by 12, and this will be GCD 6 by 0, and once I hit a 0, I stop and I say that, so that is 6. Okay. What happened? If I assume that the problem size is the larger number here, so first I reduced 42 to 30. So there is a decrease of 12, right? From 30, I go to this large number again. I have another decrease of 12, right? Right? Yes, and then from 18, I go to 6. Now my decrease size is equal to 6, and from that 6 to from 18 to 12, there is a difference of 6, and that difference propagates on the next one. So n decreases in variable steps. So that is why we call this decreasing the size by variable amount. But I think the next example will make it more clear and more intuitive for you to understand variable size decrease. And I find it very useful in practice as well. Let's remember the binary search. Binary search is very nice, right? You are given a sorted sequence. You start from the middle and at most in log n steps. So you find a key, or you find that it's not in your sorted array. But let's think about something from real life. Okay, so I have a dictionary and I'm looking for a word that starts, say, with letter B. When I am looking for something starting with B, I do not start my search in the middle of the sequence. I know that it is closer to the beginning than the end, right? And how I get this intuition? Because I know the first key is A and the last key is Z, and I'm B, it should be closer to the beginning. An interpolation search just follows this observation. It tells us that while running your binary search, instead of landing on the middle position all the time, just make an interpolation to find the index of this middle term. In other words, by considering the beginning and end of the current sequence, try to guess where your key might be closer to, and accordingly you update it. Okay, so let me try to describe it on a figure. So let's assume this is my array. Okay, so this is my array. This is my leftmost position. This is my rightmost position. They have the AL and AR values there. In my figure, I will say that, so this is the index. Okay, so this is the index of L, which includes the value of AL. And this is the index R, which includes the value of AR. What I am looking for? I'm looking for V. V is somewhere here, okay? So V is somewhere here, and I will assume that the keys, the elements in the array, so they are just a linear line. I know this is not always true, but I will like to just try to come close, okay? And if I make this assumption, then what I am curious is, I would like to find position X, because in my binary search procedure, instead of going to that middle element, I will go to position X. I know L, I know R, okay, I know AL, I know AR, I'm given V, but I don't know what X is. I'm trying to guess it. How I can do it? So if we assume that this is linear, then there is this angle theta, and the tangent of this theta with the big triangle, so it is this one, right? AR minus AL divided by R minus L. So this is equal to tangent theta, right? Similarly, on the small triangle, it will equal to, so this part is equal to V minus AL, it is here, right? And what is this? This is equal to X minus L. This is again tangent theta. Okay, these two guys are equal to each other. If you solve this equation, you will see that X is equal to that one. That means whenever I am doing my search, I have my L position, I have my R position and corresponding values, and I'm looking for what V is. Instead of going and checking the middle guy, I will compute X, and wherever it points to, I will go and check the key value with that guy. Again, the rest of the procedure, it is the same. If that key is greater than the element at position X, then I should consider the right partition, otherwise the left partition. So that is the interpolation search. And with the interpolation search, you see my decrease in the input size is not constant, is not a factor, but it is a variable amount that you cannot know unless you start this search on the real data. So that's a variable size decrease in the input space. That concludes our discussions. Let me see if I have any more slides. No, yeah, okay.